Hey Andrew, thanks for taking my call.
Hey Ethan, no problem. What's up?
I've been thinking a bit about how we reason about effects in information flow recently, and I know you think a lot about effects. Can I ask you some questions?
Yeah, absolutely. Can we start with you explaining information flow to me?
Sure. Let me grab a virtual whiteboard so you can see what I'm talking about. The core idea is that we add a new type constructor, this L sub L of tau thing, that represents labeling a type tau with a security policy L. The most common policies are confidentiality, so this might be secret or public. Usually, information flow labels form a lattice, but all that really matters is that they form a preorder. So here, public data can influence secret data, but not vice versa. In order to use this to reason about security, we define a relation that we write like this to express the idea that information labeled with label L can influence data of type tau. That means that either tau is a labeled type with label L prime, where L flows to L prime, or L can influence all of the constituent parts of tau. For example, if L can influence tau 1 and tau 2, then L can influence their product. Note that no label can influence a sum type, since which side of the sum actually appears is data in and of itself. The relation also allows us to add an elimination rule for the labeled type constructor we added earlier. The rule says that if E1 has some labeled type, L sub L of tau 1, and E2 uses a tau 1 to produce a tau 2, then we can take the output of E1 and rip off the label and use it in E2. We just need to make sure that data labeled L can influence data of type tau 2. That way we're sure that we're using labeled data in accordance with its security policy.
Okay, that makes sense. But you were asking me about effects. What if we look at some labeled data, and based on the results, we perform a different effect? For instance, what if I look at a secret boolean, and if it's true, I write 0 to some state, and if it's false, I write 1. This produces the same value either way, but now any adversary who can see the state can tell exactly what the secret data was.
Yeah, that's a well-known problem. What we do is we keep track of an extra label in every typing judgment. The label keeps track of how sensitive the control flow is. That is, how much secret data has been used to determine whether or not we execute this instruction. We call this the ProgramCounter label, or the PC label. Then we don't allow any effects that might leak information based on the sensitivity of the context. For instance, we won't allow you to write to state unless any adversary who can see the state can also see the information that has affected the control flow. Let's say you have to be able to read some label, L state, to see the state. Then, for a write to type check, it would have to be the case that the PC flows to L state. However, you should be able to read state no matter what the context is, so that rule doesn't have the same restriction. Of course, we also need to update the PC label somewhere. We do that in the unlabel rule because data can affect your decisions after you unlabel it. We just raise the PC by L in the E2 branch of the original rule, and that's sufficient.
Okay, this looks like it would work, but now this unlabeled thing seems really imprecise.
Yeah, it looks imprecise, but it turns out it's not. This is something called coarse-grained style, which is actually equivalent to a fine-grained style that doesn't unlabel data before computing on it, and only raises the PC label when you branch the control flow. It also turns out the same reasoning works for throwing and catching exceptions. We just need a label that describes who can see if the computation aborted. Oh, there's actually another way of thinking about the PC label that I think you'll really like. The PC label is a bound on the effects an expression can produce.
Interesting. That's not how I'm used to thinking about effects.
Oh? What would you do?
Well, I'm used to using monads to reason about effects.
How do those work? Can you explain it to me?
Sure. The idea is that we split into two worlds, the effectful world, to which we want to give semantics, and the pure world, which we already understand the semantics of. We then find a function m from effectful types to pure types and a translation from effectful programs to pure programs. The translation takes programs of type tau to programs of type im of tau. For example, if I had a program E which can read and write state, I can transform it into a program that produces a function from states to outputs with states. So, im would produce appropriate arrow types. In particular, I can take a program that reads state to a function that takes a state and just returns it. I can also take a program that writes state to a program that takes some input state, ignores it, and returns whatever was written to the state.
Okay, so in the information flow world, we could make the state a labeled type. That way, every program that writes to state can only use data that's allowed to affect the state. If we look at the example program you had earlier, we can translate it to something like this. Oh, cool. Now we can reject this insecure program without using a program counter label. We just have to look at the program output.
Yeah, by making the effect explicit in the types, we make it a lot easier to reason about.
Okay, I like this, but it does seem like a lot of work for a compiler. The program counter label method has an obvious implementation.
Yeah, it turns out that what we do in compilers is a technique called type and effect systems. What these do is they add to every typing judgment an extra annotation describing the effects that are possible in the program. So, for instance, we might allow programs to have effects that are subsets of reading and writing. Then, clearly the program that reads state will have the same type as state and be able to also have a read effect. The program that writes to state will have type unit and will execute a write effect in addition to whatever effects are run by the expression written to state.
Right, that makes sense. It also seems like since the monad you gave earlier made sure everything was secure, we should be able to create a secure type and effect system.
Yeah, I think we can. It seems like we'll need to change the unlabel rule. After all, that was the only place where we checked the program counter label. Instead, we should go ahead and make sure that the output of the program being unlabeled can flow into some appropriate label, but I don't know what that would be.
Well, when we're dealing with state, usually we just assume that every state cell has a type that expresses its security condition. Before, we just had one state cell, so that was just one label. Generalizing that, it seems like we could go ahead and assume there's a label for every effect, describing who can see the output of that effect.
That makes sense. Okay, so let's assume that there's a function L from effects to labels. To be nice, we can go ahead and write it with a subscript syntax. So I would write L of epsilon as L subscript epsilon. With this, we can go ahead and rewrite the unlabeled rule for a secure type and effect system.
All right. It seems like for multiple effects, I can just go ahead and add this, right? That's really cool, since usually combining effects in information flow can be complicated.
Yeah, you can, but the semantics are going to change.
Oh? How?
Well, with a single effect, we can just use a monad. But even just distinguishing between read and write effects means that we need something more. It turns out that in a lot of cases, an indexed monad is good enough. An indexed monad is defined over a lattice of effects, where the sequence of two programs with effects epsilon 1 and epsilon 2 has the join of the two effects.
Wait, I don't think indexed monads are good enough for exceptions in state. Since they use a lattice, we have to be able to sequence any pair of effects. But what happens if we sequence this program that throws an exception only when a secret is true with this other program that modifies the state? If the secret's true, then the first program throws an exception and the write never happens. So any adversary who can see the state can also see if we threw an exception. I see two ways to fix this. We can either have the label of the exception flow into the label of the state, so it doesn't matter that the adversary can see if an exception was thrown. Or we could use a partial algebra of effects. To compose a program that can throw an exception with a second program, the label of the exception has to flow into the label of the effects of the second program.
Okay, that's a good point. What we can do is to generalize what's called a productor, which is defined over what's called an effector of effects. Effectors are kind of like monoids, but instead of a binary function, they use a relation between a list of input effects and an output effect. That way, we know how we can treat a big sequential composition of effectful programs. While index monads are good for a lot of day-to-day type and effect systems, it seems like once we start looking at security, partiality can be really helpful. For that, we should use a productor.
Okay, this is cool, but I'm not sure what it teaches us.
Well, maybe we can try to generalize and come up with a semantic framework.
What would that even look like?
Well, we can come up with a series of rules so that we can see when PC systems can be given our semantics. There's a series of rules that we know say that a type and effect system can be given semantics via a productor. We use it to axiomatize what effectful languages look like, so we can reason about many languages at once. Maybe we can add ideas about information flow into that, so we can reason about secure languages all together.
Sure, that sounds interesting. Can you give me a sense of what these rules look like?
Of course, we have two languages like before. One is pure, and we understand its semantics. The other is a language with a type and effect system. The pure program has sequential composition, so we can feed the output of one program as the input of another. In the effectful world, we can do the same thing, but now the whole program needs an effect. We can determine this by applying an effector relation to the effects of the programs being composed. The other key rule lets us transform an effectful program into a pure program, changing the output type of the program. We call this capturing the effect. The rest of the rules tell us how sequential composition and capturing play with each other. What do you think we should add to this in order to reason about information flow?
Well, it seems to me like the most important part of information flow is the relation defining when an information flow label can influence a type. It's defining the security of the type. If we're using this transformation to capture effects in output types, that probably means we should know what labels can influence the transformed types. It seems like to influence a transformed type, a label needs to be able to influence not just the original type, but also the effect.
Yeah, that makes sense. Could the rule be as simple as if L can influence tau and L flows into the label of epsilon, then L can influence the productor applied to tau and epsilon?
Yeah, I think that makes sense.
Okay, how do we validate this rule?
It would be really nice if we could show that a type and effect system is secure, assuming that the pure language is.
That makes sense. But can you explain what the security theorem would look like?
Sure. We usually want something called noninterference. The basic idea is to run the program twice with two different secret inputs. Then, noninterference says that the outputs have to be low equivalent. That means that any public parts of the two outputs, including their effects, have to be the same as each other.
Okay, so it seems like you have a notion of low equivalence that takes care of both values and effects, but it seems like we'll need something similar for the pure language.
Yeah, for the pure language, it just needs to look at values.
Okay, so let's abstract a step further. We have a form of equivalence up to a label for both the pure and the effectful language. Then we need to know that capturing the effects of effectful programs doesn't cause things to become equivalent that weren't before.
Great. So what does this tell us about noninterference?
Right, let's abstract that too. In our framework, we don't have values, we just have programs, but programs produce values. Instead of secret inputs, let's have two programs, P and Q, with the same secret output type and secret effects. Then, if we sequence P or Q with a third program, R, then R is non-interfering if it produces the same public outputs, no matter what P and Q we pick. So, we want to use this general version of non-interference to show that all programs in languages that fit our framework are non-interfering. Well, if all the pure programs are non-interfering, then capturing the effects in an effectful program gives us a non-interfering pure program. But we need to know that we haven't accidentally made things equivalent by doing the capturing, which is exactly what the rule I suggested gives us. Here's the really cool thing. For any pair of languages that omit the rules that we had earlier, plus this new rule I've been arguing for, if the pure language is non-interfering, so is the effectful one.
Wow, that is really cool. But what about the PC system? Usually when I prove non-interference, I use the PC to prove a confinement lemma. If a program type checks with a high security PC, then all of its effects must be high security. So if the PC doesn't allow writes, then the program won't write to state, and similarly for exceptions. I suppose we can see this with the type and effect system. If any program that type checks in the PC system also type checks in the type and effect system with an appropriate effect.
Yeah, it seems to me like the most important thing there is that if something is well typed in the PC system, then it's also well typed in the type and effect system, even ignoring the appropriate effect part. After all, both systems type effectful programs, and we know that our type and effect system is secure. Furthermore, we can prove that, along with the rules we gave earlier, this is enough to get non-interference of the PC system. I think we should call this theorem non-interference half-off, since it says that you can separate concerns to prove non-interference, prove non-interference for pure programs, and then provide a semantics of effects. That way, things don't get all tangled up.
That's really cool. After all, usually dealing with effects is one of the hardest parts of proving non-interference. But I'm a bit concerned we've overspecialized. Does this work for anything other than the type of state and exceptions we've seen here?
Well, let's try it on another effect.
Okay, what other effect should we try?
Well, non-termination is usually pretty easy to mess around with.
Wait, non-termination isn't an effect, is it?
Sure it is. We can pretty easily create a monad for it in the semantics, and a type and effect system for non-termination is also pretty easy. But doing it with types requires having a type that represents a non-terminating version of another type.
Actually, I know a perfect system. The first coarse-grained information flow system was called DCC and had pointed types. The idea was that every type tau also had a type tau bottom, which is tau with non-termination. Then they only allowed fixed points on these types. Is that what you're talking about?
Yeah, I think that sounds perfect. Let's create a language with unrestricted fixed points, like you'd find in any language today, and create a PC system and a type and effect system for it. We can also give a translation into the pure system using these tau bottoms as a monad.
So we translate like this. But that translation seems to fail with DCC, since no labels can influence the non-termination monad. The creators of DCC didn't want termination behavior to leak secrets, so they made sure only unlabeled data could influence non-termination. I suppose we could just say only public can influence tau bottom. Come to think of it, the potential non-termination label you used earlier actually already specifies who can see if the program terminates. We could add this allowed influence rule to make it fit the framework. It just says that data can influence a possibly non-terminating program if it's already visible to anyone who can see non-termination, and it can influence the original output.
Good point. Okay, with that fix, we can apply the non-interference half-off theorem and get a non-interference theorem with non-termination.
Wait, I recognize this theorem. If we set the label of non-termination to public, this is termination-sensitive non-interference. That's usually considered to be a really hard theorem to work with, but it seems a lot easier here.
Okay, so this seems like really good stuff. Want to write a paper?
Yeah, I would. Just to sum up, We showed that ProgramCounter Labels can be given semantics via secure effects, which are given semantics using Productors. We created a semantic framework that gives ProgramCounter Labels this semantics. We showed that the framework can be used for common effects and combinations of effects, like state and exceptions and non-termination. We developed the noninterference half-off theorem, and we showed that applying that theorem to non-termination gives us termination sensitivity, which unifies termination sensitivity with reasoning about effects. Is there anything else?
Yeah, I think for the paper we can do a bit more. In particular, does every PC system that fits our framework treat the PC as bound on effects? I bet we can come up with a counterexample, but we should be able to find a few simple rules to make bounding work. Also, in the confinement limits you showed me, we mapped the PC back to an effect. That seems like some sort of Galois connection. Can we explore what that does?
Yeah, I'll bet we can answer those questions for a paper. Thanks, Andrew. Bye.
Bye, Ethan.